September. So there will be two sessions. The first session, just your presentation for 45 minutes maximum, and then it will be followed by the session.
Okay. Thank you so much.
Mr. Wael Labidi.
Thank you. Hello everybody, my name is Wael Labidi, and I'm here to present for you the work done during my PhD on smart grid-aware radio engineering and 5G mobile networks. This thesis was co-directed by Mr. Tijani Shahid and Mr. Salahuddin Layoubi at Telecom SudParis. So here is the outline. So I will start with an introduction. I will introduce the concept of smart grid and show the interaction between mobile network operator and the grid in both reliable and non-reliable grid environments. Then I will go to treat the long-term equipment dimensioning for a mobile network operator powered by a reliable smart grid. So here it is about an optimal dimensioning of the storage and energy production unit for the mobile network operator. Then I will move to the short-term optimal battery management for electricity arbitrage and trading in the context of smart grid. Then I will finish by a conclusion, and I will give some future perspectives for this work. So let's start with the introduction. The electrical grid has the aim to deliver electricity to all the consumers in the grid, and so it is composed of generation capabilities. So to generate power, the transmission line to carry the high voltage electricity, the distribution line to carry the electricity to the houses or factories, and the smart grid network is a communication network integrated with the electrical grid in order to collect, analyze data about power transmission, distribution, and consumption. And this smart grid has the aim to ensure the balance between the electricity supply and the demand. It has also to give the right infrastructure in order to allow information exchange between aggregator or the generator of electricity and consumers. And it has also to propose some new methods for smart tarification of electricity processes. We can cite real-time pricing or demand response that I will treat later during this presentation. So we have another player, and we are really concerned more about this player. And this player is the mobile network operator who has to be continuously powered by the grid with no interruption. So it has to ensure all users' satisfaction, especially with the increase of services and the demand in data rates. And to do so and to be powered, it have to pay any price fixed by the grid, even if it is so high. And we know now, because the traffic, the user traffic is increasing, the energy consumption of mobile network, and especially the radio access network, is really increasing, and also the electricity bill on short and on long term. So our aim here is to give the right strategy and to propose the right strategy for mobile network operator in order to reduce its energy expenses on the short term and on the long term. So here I will present the interaction between a mobile network operator and the smart grid. Here in this case, the grid is 100% reliable. He can sustain without any problem the needs of the mobile network operator. So the mobile network operator have some base stations. These base stations can be powered by the grid or powered by its own battery. And so in this case, the MNO have to be endowed with this battery, and this battery can be charged directly from the grid. And if it is allowed to, it can sell electricity back to the grid. And so in this scenario, the MNO can act as a simple consumer in the grid. And so he's not allowed to sell electricity back. And so in order to reduce its expenses, it has to perform what we call electricity arbitrage. Electricity arbitrage, it consists at buying electricity at low prices and use the battery when the prices goes very high. The MNO also can be promoted to the role of a prosumer. And so in that case, he will perform what we call electricity trading. And so he can, when the prices go up, use its battery or sell electricity back to the grid. Another feature is to be included in what we call incentive-based demand response. And so in the scenarios, the grid can ask big consumers to reduce their consumption or to stop their consumption from the grid for a certain period. And the operator has to respond to the request of the grid. He can respond to the request, so everything is okay. If he don't accept the request of the grid, he has to pay a penalty to the grid. And so, in order to do so, the operator is endowed with the battery, and the battery here can be a tool in order to ensure electricity arbitrage. So, in that case, the battery will play the role of an alternative power sources in case when the electricity prices go very, very high. The battery also will allow the operator to respond to the grid request in case of demand response. And so, if the grid asks you to stop consuming from the grid, I will just turn my my infrastructure on the battery. And the battery also has to keep ensuring the functionality of backup in case of power failure. Even if this power failure in the case of reliable grid happens seldomly, but this feature should be maintained, and it was maintained in this work. The operator also can invest in a DCAC inverter. A DCAC inverter will convert the direct current, which is in the battery, to an alternative current to be able to inject it on the transmission lines and sell it back to the grid. And so the DCAC inverter will be an additional tool for the operator in order to ensure trading and so make more money from this strategy. So here is the case of unreliable grid, and so the MNO has this obligation to be powered with no interruption, even if the grid may suffer from multiple power failures. And as the grid now cannot be trusted, the operator has no other choice by developing what we call a virtual power plant. And in that case, this virtual power plant consists of the aggregation of multiple hybrid power sources. So we can cite the photovoltaic panels for solar power production. And so this photovoltaic panel can power directly the NodeB. The battery, in our case, will store the excess power energy and power the infrastructure when the renewable energy cannot sustain the demands of the operator. And the operator also have to ensure a backup solution, which is now the diesel engine in order to prevent power shortage when there is not enough energy reserves in the battery. So the thesis objective is clear. We have only to minimize, but not only, to minimize the total cost of ownership of the operator. The total cost of ownership is the sum of the capital expenditure and the operational expenditure. In our case, the capital expenditure is the money invested by the operator in order to buy equipment. So it is the price of the battery, the price of DCAC inverter, the price of diesel engine and PV panels in case of African Sub-Saharan countries. And in order to optimize the CapEx, we will propose a long-term strategy in order to decide the right dimensioning of this equipment and so minimize the TCO. The OPEX in our case is the daily energy expenditure for network operation. It is the money that the operator will spend in order to have electricity for each day. And this OPEX, it will be optimized on a short term by performing the techniques of electricity arbitrage, trading, or being included in demand response in case of reliable grid. So our contribution, the contribution of our thesis was to propose a two-level hierarchical optimization problem in the context of reliable smart grid environment and the context of unreliable grid environment. In the first case, we will propose on the long term, so on a period of on a long-term period of time counted in years, an optimal battery dimensioning. We have to decide the size and the type of the battery if we use lithium or lead-acid battery. The optimal cycling strategy in order to extend the battery lifetime. We know all that the battery have a limited lifetime, use it or not use it, and so the operator has really to take advantage of all the capacity of the battery by deciding the number of cycles to be performed in maximum per day. And also we have to decide whether to invest in DCAC inverter in order to be able to sell electricity back to the grid or not. And in it depends also on the fluctuation of the electricity prices here. So on the short term, we'll propose an optimal battery management strategy on a daily basis, subject to cycling and charge level constraint. This optimal battery management will allow the operator, as we told, to perform what we call electricity arbitrage and trading, and it has to take into account the fluctuation of the electricity prices, the consumption model of the NodeB because of the traffic, and also some constraint on the cycling and of the battery. So we will fix constraint on the number for the maximum number of cycles, and also a charge level constraint for the battery. On the short term too, we proposed this optimal battery management for in order to be able to ensure demand response services. We will not treat it in this presentation because we don't have enough time for that, and we added also another layer of complexity in order the operator is allowed to delay some traffic that we call delay tolerant traffic. As example, the application updates, and in that case the operator has also to decide when to process this traffic in order to minimize its energy consumption and minimize its energy bill. In the case of unreliable grid environment, we will not also treat it in this presentation. We have to decide on the long term an optimal dimensioning of the battery and PV panels. The sizes of the PV and the battery have to be compliant with each other in order to reduce the TCO of the operator. And we proposed on the short-term usage of hybrid power sources that extends the battery lifetime, and so minimize the cost of the operator by taking advantage of the renewable energy potential in sub-Saharan countries. So here I will treat the first section on the long-term equipment dimensioning for mobile network operator powered by a smart grid, by a reliable smart grid. So the settings here, so we will assume that the MNO can act, he acts as a consumer, and he can even act as a prosumer in the smart grid if it is allowed to, so if it is allowed to sell electricity back to the grid. The MNO sites are endowed with a battery, with a DC inverter. The battery will ensure both functionality of backup and electricity arbitrage and trading. The battery has usage constraints on their level of charge. The operating level of charge have constraint on their lifetime and may suffer from degradation, used or not used. The traffic is increasing from one semester to another, and if we go back for the report of Cisco, we know that the traffic is increasing on average by 44% a year, so which means a big increase in the operator energy consumption. Also, the electricity daily prices changes from a semester to another. So the profiles of the electricity prices can change with respect to the grid owner policy for energy generation. So in some country, if we turn more for renewable electricity, we'll find that the prices when there is enough generation will be low, and when when there is not enough generation, the price will go high in order to give incentives to the consumer to shift their consumption on the other periods. So our objective is to minimize the total cost of ownership in a period counted on years, and we take an example of 10 years. So we formulate this problem as a Markov decision process. A Markov decision process, we have the Markovian property, so there is only one time-step correlation, and in which we can also decide some action, and it is a process because he lasts in time. And so in our case, the optimization window will be 10 years, and the operator has to decide on its battery, on its equipment dimensioning and cycling on a time step of 6 months. The status of our system is the size of the battery. that we have already on site. It is the calendar age of the battery, so the number of years from the battery was functioning. The cycle age, so in this case, it is the remaining cycles that the battery could perform before being considered unusable, and if the trading is on and off, and so in that case, if we are already on load with the DC-AC inverter or not. So the actions here will be the battery size to install and the maximum number of cycles per day, and if we install a DC-AC inverter. In fact, we can even choose to keep our actual battery if it's still functioning. We can replace our actual battery by a new one and decide its size, and on the maximum number of cycles. So we have like to fix per day for each day of the semester a maximum number of cycles to don't cross. If we choose it equal to 0, so we can already have a battery and force our system to be exclusively powered by the grid. The transition probability in our case are all deterministic, but we can add randomness if we include the electricity prices profile and the user profile on the state space, and we can even define some correlation between the prices from a semester to another. The outcome here, it is the money spent by the operator per semester, and it is the sum of the capex, which is E in our case, so the investment cost of equipment, and the OPEX, which is the sum of the maintenance cost and the money spent by the operator for its daily operation multiplied by 180, which are the number of days in a semester. D in our case will be calculated after doing the short-term optimization, and so D should be in our case evaluated for all the configuration of sites, for all the battery sizes, for all the ages of battery, and if we are able to sell electricity back or not to the grid. So in order to solve this Markov decision process, we proposed a linear programming solution in order to find the optimal occupation measure beta. The occupation measure, it is defined as the probability of a system to be in a predefined state, and that he performed one action A. And we will calculate this occupation measure for all the couples states action for all the time slots for all the semesters. And so our objective here, it is to minimize the sum of the money spent by operator per semester. So the money spent by the operator on the long period of time, which is 10 years. And which is the TCO. So we have 4 constraints. The 4 constraint ensures the sum of all the occupation measures is equal to 1. The second constraint put a link between the transition probability of the Markov chain and the occupation measures. The third constraint have to ensure that some actions cannot be done. There are some actions which are possible in some states. Example, if we assume that the battery still have only 180 cycles to be performed before being considered unusable, we cannot perform 2 cycles per day, and so perform 360 cycles in a semester. And the last constraint have to ensure that the occupation measure as the first semester is equal to an initial distribution that we use, and so we use that the operator at the beginning of this optimization window has no battery, has no DC-AC inverter, and so has no other choice by being powered exclusively by the grid. After having this optimal occupation measure, we can calculate, we can obtain optimal randomized policy, which defined for each state of the system and for each semester, each time slot, the probability of performing an action in a state. And so this probability is equal to the occupation measure of the couple state and action divided by the sum on all the action of the occupation measure of all the states and action. So here we go for the short-term optimal battery management strategy, and this part will allow us to calculate what we presented as D in before the last slide. So our objective here is to minimize the operational expenditure. So we will minimize the MNO daily expenditure by performing electricity arbitrage and trading, in addition to ensuring the functionality of backup. For a battery with capacity or a size denoted Bmax, decided by the long-term optimization, so the decision on the battery dimensioning, and for a certain age, a cycling life and the calendar life of the battery. We have also a constraint to maintain the battery state of charge, which is the level of energy in the battery between a minimal and a maximal value, which extend the battery performances and can extend its lifetime. So, and it depends and the change from a type of battery to another. The battery also should not perform more than gamma C cycles per day, and gamma C also was imposed by the long-term cycling strategy. So we will say the operator per day will not perform more than 2 cycles. This is done by deciding at each for each hour of the day the source to power the MNO, if we use the grid or we use our battery, and the amount of energy to be bought or sold from the grid for trading or for arbitrage. So we formulate the problem also as a Markov decision process. Here, the decision time step is 1 hour, so we will decide the source for 1 hour. And the optimization window is 1 day, so 24 hours. The states here, SH, are composed of the battery state of charge, the level of energy in the battery, the electricity unitary prices, which is fixed by the grid, the traffic load, the user traffic load in the cell, the charge and discharge state of the battery in the previous time step. So if the battery wasn't charging or discharging before, and the number of remaining cycles. In fact, if we, example, impose 2 cycles per day for the battery to be performed, this value H at time slot 0 will be equal to 2 cycles. So if we assume that we was in discharge and we did a charge, this value will go to 1.5. And then in order to ensure the constraint, this value H should be maintained above or equal to 0. One of the most important equation in this to characterize the state space, it is the evolution of the battery state of charge. So the battery state of charge at our H plus 1, it is the battery state of charge at our H plus the amount of energy which is bought or sold from the grid. So this amount depends on the energy on the battery discharge energy efficiency, which are the losses when the operator is when the battery is discharging, the losses of energy. And also it depends on the energy consumed by the NodeB in order to ensure its operation. And we can see that this value depends on the battery energy efficiency, and it has like 2 components: a fixed part and dependent of the traffic, and a variable part which is dependent of the traffic. So the actions here are the energy source and the amount of energy to buy to sell. This transition probability, it is the probability for the system to be in state SH plus 1, knowing that he was in state SH and that he performed the next in AH. And here, the battery state of charge, the charge and discharge state, and the number of remaining cycles are known if we know the state and the action that we did before. But the randomness here comes from the distribution of the traffic load and the electricity prices. So we can assume different distribution, some correlation between them, and then include it in the model, and the models stay available. We have the instantaneous reward or our outcome, and it is defined as the money spent or earned per hour by the operator. And it seems like the battery, and so it is the price of the electricity multiplied by the amount of energy bought or sold to the grid. Here we assume that the prices of selling electricity are equal to the prices of buying them, and also the money that the operator should pay to the grid in order to power its infrastructure directly by the grid if he wants to. So in order to solve this MDP here, we will propose another method, and we will apply policy iteration technique. Policy iteration technique have the aim to achieve a deterministic policy, mu bar, which is composed, which is a vector of some subjective function from each time step from 0 until n-1. Each one of them define for each state of the system only one action to perform. So for each state, we will have one source of electricity and one amount to buy or sell. This policy iteration technique is based on solving a Bellman optimality equation with a backward recursion from step n-1 to 0, assuming that what we call, and we will present later, the cost to go, the n to s at time slot n is equal to 0. So to do this policy iteration technique, it is based on two main equations. We will have the policy improvement step, and in that step, we have like to find the optimal action to be performed at time step k for each state of the system s. And here we can see the optimal action to do at state s in time slot k. It will minimize the instantaneous outcome at time slot k, and here what we call a cost to go from time step k plus 1 until the end of our system, so time step n. This value will be calculated and updated using policy evaluation step. And here, as we said, we will evaluate the cost to go for each state S from step K to N after choosing policy mu K. And the cost to go at time slot K, it is the money that we spend in time slot K plus the cost to go from K plus 1 until N. So until we will arrive at time slot 0. And the optimal daily MNO expenditure, in this case, it is obtained by just getting the value of the cost to go from time step 0 to time step n for the state S0, with S0 is the initial state of our system. Here we assume that the battery is empty at the beginning, and it was a discharge step, and the remaining cycling is gamma C at the beginning of at h equal to 0. So here I will go to present the short-term numerical setting, and here we will have two case of studies, Danish and EPEC zone electricity market during summer and winter. We will have a higher electricity prices variation in winter compared to summer. It is because of the heating, and so we consume more in Europe because of the heating, and so that's why the prices are higher in winter. And also there is more variation in Denmark compared to EPEC zone, because in Denmark they rely on 42% of their energy supply is relying on wind turbine. And so this energy source is not that controllable compared, for example, to nuclear power, and that's why we will have a high variation between the daily prices. The real daily electricity prices will be predicted from what we call day-ahead prices for spot and retail prices. There are prices which are fixed by stakeholders in the electricity market in order to allow bidders to make their bids for electricity. And so our prices will be predicted based on that prices, and also we can use some machine learning techniques in order to predict the prices from previous history, the week before or the month before, the year before. So we will do this work for two battery types with different usage constraints. We will choose lead-acid batteries, and the lead-acid have the constraint for the state of charge to be between 50% and 100% of the battery capacity. We have a C rate, which has to be lower or equal to 0.5 C, so we cannot charge the battery more than 50% during 1 hour. And the battery is cheap, so this technology is cheap, but it has some problems because it has a low energy efficiency, so there are very, very high losses in the processes of charging and discharging the battery. Lithium is a more expensive technology with better performance. The state of charge should remain between 20 and 90% of the battery capacity, so allowing us to make trading with higher amounts of energy. And this rate should be lower or equal to 0.7 C, with higher energy efficiency estimated to be 94%. The operating operator have the, we will simulate the result for 3 battery sizes in 16, 32, and 42 kilowatt hour. And we will impose a constraint on the number of cycles per day to be equal 0, 1, 2. So we cannot, and so if we fix the constraint to 0, so we force the system to be powered exclusively by the grid. So here we start with the case of Denmark in summer when selling is not enabled with 32 kilowatt hour battery. So we will present the result for lead acid and lithium battery. So if you see the figure above, we will have the electricity prices in Denmark in summer drawn in blue. The user traffic, it is in black. For the curve below, we will present the average state of charge of the battery for the blue for a lead-acid battery of 32 kilowatt hour when we impose the constraint on the cycling strategy of 1 cycle. A lead-acid battery of 32 kilowatt hour with a constraint of 2. The green one is for lithium with 1 cycle, and the black one is for lithium with 2 cycles. And we see here clearly that the state of charge limitations were respected for all types of battery, and that the constraint on the number of cycles were matched in all the cases. So if we impose to the system to don't do more than 2 cycles, we see that in average the operator did in average 2 cycles. We can also see that the charging comes at the minimum prices here for the first time. And here, if we have another local minima, so we see that the second charging was happening here. So it proves that our policy take advantage of the electricity price variation. Sorry. So here we will see the effect of energy selling. So we will compare the state of charge for the cases when the MNO is allowed to sell electricity back to the grid and when it's not. But here it will be the case of Europe EPEC zone. So it is a zone of 28 countries, and France is among them too. And so here the prices variation is not that high if you see compared to Denmark. And here example, if we see the red curve for a lead-acid battery that we imposed 2 cycles as a constraint and who is not allowed to sell, even if we imposed 2 cycles, the operator the battery performed only 1 cycle on average, because there was no gain to perform a second cycle, especially because the electricity prices have one peak of peak structure. So there is no big variation here in order to make a second cycle. We can see also that the operator favors more cycles when selling is enabled. Here we will summarize the result on the short term, and we have found out that there is more energy bill saving in Denmark compared to Europe, because there is higher price variation. The MNO favors performing more cycles in Denmark for the same reason. Lithium outperforms lead-acid battery because it have better energy efficiency and higher state of charge operation. There is more energy bill saving when selling is enabled. It's normal. And there is more cycles, but the problem when we perform more cycles, even if we make more gain, but we will lower the battery lifetime. And that's why we have just to see the effect of electricity arbitrage and trading on the long term. So here are the numerical settings for the long-term strategy. Here, as we told, it will be an optimization over 10 years with a decision time step of 6 months. And the operator has a choice to install 3 battery different sizes, 48, 64, and 80 kilowatt hour for arbitrage and trading. And it has also to keep a battery, to keep 50% of 50 kilowatt hour for backup functionality. We can here see the performances of lead-acid and lithium battery. We assumed that the calendar life of lead-acid and lithium battery here is 10 years, but in reality, the right values is 6 years for lead-acid. Lithium can reach 10 years, but yeah. And we assumed the prices of lead-acid battery equal to 160 euros per kilowatt hour compared to lithium battery. But we can see that lithium have more, gives the opportunity to more cycles with higher DOD, with higher depth of discharge. And we can see that the charge and discharge energy efficiency, it was taken to be linear, and it decreased with the battery lifetime. For lead-acid battery, it is between 86 to 80%. When we reach 80%, we assume that the battery has to be removed. And for lithium, it keeps a good energy efficiency between 96 and 92%. So we assume that there is a traffic load increasing, that the traffic load is increasing from semester to another. And we assumed two models of this traffic increase. We took a case of when the traffic is exponentially increasing and when the increase is more incremental. Here also, we will see the usage of our battery. If we install a lead-acid battery, we will allocate between 50% and the state of charge between 50% and 100% for arbitrage or trading, and the state of charge between 0 and 50% will be allocated for backup. It will be rarely solicited, and so the battery will not degrade because of backup. And so if we decide to install a 80 kilowatt-hour lead-acid battery, and we assume at the beginning that we'll allocate 50% for backup, so we will have only just to add 10 kilowatt-hour in order to ensure this 100%. And that's why you can understand the TCO saving. We assumed also that the DCAC inverter have an installation price of 1,000 euros with 10 years calendar life. Selling and buying prices have linear relationship with coefficient in 0, 6, 0, 8, and 1. Here we assume that the selling prices are lower than the buying prices because we assume that the grid can sustain with no problem the needs of its consumer, and so he has no incentive to buy electricity from others, and so the prices cannot be higher. And we assume the maintenance fees equal to 0 for all equipment, but in the model it can support if we put it not 0. So the prices increases and have a seasonality trend. We will take we can see example here, the prices in winter in Europe growth. You see, so the blue curve is the prices for the first year. This is the prices considered in the short term. And here we can see that the increase is seen on all the hours of the day because we don't use that. Even if we are turning more to renewable energy, the importance of controllable energy sources as nuclear is still very, very important in these countries. In Denmark, as we assume that the country will go more and more for renewable electricity, the increase of the prices are more visible in these two regions. Compared to, in this peak region. So when the consumption is higher in order to incite consumer to shift their consumption. So here we will have some results. The long-term investment plan of the operator will look like this. So we will take the European market when the MNO is acting as a simple consumer of the grid. He cannot sell electricity, and we can see that when we took the real equipment prices, the decision was to don't install any battery for backup and trading and remain powered exclusively by the grid on the whole time on this period of 10 years. We tried then to find the minimum prices of equipment that we should negotiate in order to find an equal gain compared to when powered exclusively by the grid. And here we should negotiate a lead-acid battery with 90 euros per kilowatt hour, and for lithium 210 euros per kilowatt hour. And here we can see that it install a battery of 48 kilowatt hour in the winter of the first year and use it until the end of calendar and cycle life. And here we can evaluate the TCO gain. The TCO when this new battery is only used for arbitrage. So and here we will have this TCO. The saving was 0.12, And when the battery is used for arbitrage and backup, so it reduces the initial investment and backup, we can achieve a saving of 3.44%. In the Danish market, the electricity variation is higher, and so the gain is really, really higher. And so here we can say that we can even achieve 22% gain in the case when selling is a load with the real equipment price. When selling is not a load, we will achieve lower gain, which is normal. Here, if we focus on the optimal cycling strategy of the battery, we can see here it is the years, so in these tables. And we can here see the number of cycles that should be performed per day by the battery. So it is 1 and 2, 2. So, and in all our cases, the operator uses to the maximum the cycling capacity of its battery. So, and we can see even in some cases when the electricity is low, that the operator can even install 2 batteries, and the last one doesn't even last for 2.5 years in case of lead acid. You can see. So we don't have even to reach the battery calendar life because the gain was so important. So here I will go for the conclusion and the future perspectives. So we presented the study, an energy management strategy for mobile network operator in context of reliable and unreliable grid. So on the long term, we proposed an optimal equipment investment strategy. So we decide the time to install equipment. We decide the dimensioning of this equipment, and we decide the long cycling strategy of our battery in order to take advantage of it and extend its lifetime. On the short term, optimal energy management, we proposed the battery users that reduce the operational expenditure of the operator by taking advantage of electricity arbitrage and trading, and also in the case of African country, the integration of hybrid power sources in order to take advantage of the great potential of solar power. So the case of reliable grid, we saw that we can achieve a considerable financial gain on the long term compared to the case when powered exclusively by the grid by doing these operations. The electricity arbitrage and trading were taking advantage of the electricity prices fluctuation and the traffic increase, and so when the variation is higher, we can achieve a better gain. The battery usage that we propose extend the battery lifetime and maintain its performances. And for this part also, we based our work on some studies done by our colleague in European project So Green. So we included a lot of tests on battery of our colleagues. The usage of battery for the case of an incentive-based demand response, we didn't show it in this presentation, but there is it is in the thesis, allow the operator to take advantage of the incentive-based demand response, and it have a great impact on alleviate the demand on the grid at peak hour, and even it have a CO2 footprint impact, because as we can shift the consumption, we don't have to solicit some very polluting power sources. Oh, sorry. We proposed for the last part an optimal scheduling of delay tolerant traffic, and so we will process this traffic in hours when the electricity prices is low, and so we will not spend too much money, or when we have enough reserves in our battery. So and with respect to a constrained delay for the services. In the case of reliable, unreliable grid, for the short term, we propose the integration of hybrid power sources, an optimal usage of them that ensure that the battery will not perform more than 1 cycle per day, especially in this in this difficult environment with higher temperature. And on the long term, we achieved a great trade-off between the sizes of storage and energy production unit, PV panels and battery, which take advantage of all the potential of solar power and the grid reliability, and takes into account the grid reliability improvement in these countries. So as a perspective, so I will propose a method in order to apply my work in real use case by improving it and also improve the robustness of my solution. So at the beginning, we will do electricity price forecasting on 10 years. So we cannot just stick to the mathematical models. We can have some mathematical models, especially for spot prices. We have mirror version with jump diffusion. But also it has to combine mathematical models, machine learning based on heuristic data, and also some prediction based on real data. So if we know that there will be an effort of the government in investing in more renewable energy, we know that the prices model will change. If we know there will be a real estate project in the zone, we know that the consumption will increase, and so also the electricity may even increase. In order, because as you saw in the model, we assumed that there is one typical day that we do the short-term optimization based on that. So we multiply it by 180. And in fact, the idea now is just increase the robustness of our system by doing what we call electricity price classification. And so for each semester, we'll define some classes. And the classes will be chosen by comparing the difference, should take into account, in fact, the optimal policy. So example, in trading, we will buy electricity at low prices and sell them at high prices. So we just have to compare the difference between the low prices and high prices and make some classes, and then decide. This is the case of one cycle. If we are in 2 cycles, we will buy the prices in the first minimum local minima, sell them in the first local maxima, and do the same for the second cycles. And so here we have to compare the difference between the 2 minima and 2 maxima. Then we can apply the long-term optimization as presented before using linear programming. But here, we will keep the same energy, the same dimensioning of our equipment, the battery, the DC-AC inverter, but we will define a new vector of cycle constraint for each class of days. So for this class of days, we can say, okay, there is no big price variation, and so we remain exclusively powered by the grid. There is higher variation for these days, and so we do 2 cycles, and so on. Then, after applying the long-term optimization, so we we evaluate the TCO gain and make a risk analysis. For me, example, if I find a TCO gain of 1%, so probably I will have some errors. So I have no incentive to invest. Probably I will be losing. And so I have just to remain powered exclusively by the grid. If I find, example, 10% gain, so it is an interesting solution and should keep on. So if the solution is interesting, we will apply the long-term strategy as indicated by the optimization. And so we will install our battery, and we try to start our operation for electricity arbitrage and trading. And for each day of the semester, at the beginning of the day, we will predict the real prices based on day-ahead spot prices and retail prices, and also some machine learning, some heuristic data. And we compute the short-term optimal strategy for these predicted prices, and then we get the gain at the end of the day. So, and then we have to evaluate the gain semester per semester. So if we finish the first semester, I come after 6 months, I have to evaluate the equipment states. I should test my battery, see if the battery will stick to the prediction. I should, and we can increase the robustness of our solution, especially if we assume that there is a correlation between the prices in the previous semester with the prices in this semester. And we can use model predictive control in order to improve this robustness. So here are the publication lists. So I published in 1 journal paper, 3 conference papers. There is work on 4 other papers. It's work ongoing. 1 other journal paper and 3 other conference papers. Thank you so much, and thank you.
Okay, thank you. So now let us proceed with the questions.
Yeah.
To get started, we'll give the floor to Professor Nurminen from Aalto University.
Okay, thank you.
Thanks.
And thank you for the presentation and very interesting work. I'm very happy to read it, and thank you for the university as well for inviting me to participate to this interesting work. So
The pleasure is for me.
So it was really pleasure for me to look into what you have been doing and reading. So if I start with a sort of very big wide area question in a way that there's been a lot of work on this demand management.
Yeah.
How supermarkets could switch off their freezers, how households could do things at the right time and so on. So do you have some feeling how important the cellular network would be in the demand management?
And the demand.
In comparison to the others?
In fact, the problem of cellular networks, we cannot shift our consumption. We cannot shift the treatment of the services. And so, in our case, we cannot, example, for household, they can postpone, example, some pool pumping techniques to hours when the electricity is low. For the operator, the battery is the only solution in order to be able just to do this technique and participate in the demand. We can also apply some energy reduction techniques also. So.
But you had also some of the traffic delay things in.
The traffic delay. Yeah. But the problem, I think, because this traffic is not high compared to, we can delay in our case for some hours. And so if we see the traffic in software updating, it cannot constitute more than 5% of the whole traffic. And so the gain of this solution still a little bit low. For sleep modes, the problem of sleep modes, we cannot apply them for long time. And we can have some gain on short period, but on the long period, if we estimate these works, we cannot probably achieve more than this battery management strategy, but especially. But my solution is depending on the variation of the prices. In a country in France, when the prices are a little bit flat, my solution will not work. I will not have any gain. So it depends. So it's really dependent on the price variation. So it's probably good in Denmark.
Looking at it from the cost point of view from the cellular operator rather than from the flexibility point of view for the grid provider.
Yeah.
Good. Then if we look at the modeling methodology that you have been using, so you had these Markov decision processes, linear programming, policy iteration kind of things. So was it sort of obvious for you that these are the right ways to model this thing? Or did you consider many other ways to model these problems?
In fact, when we define the problem, especially because we are doing an action at each hour of the system, we said that the best modeling probably for this problem is using the fact of having flexibility, because we can have also the Markov decision process can even have can even consider some correlation between the prices and the hour before with these prices. And so we used this model in order, even if we want just to propose more complex modeling for the transition between the states, a Markov decision process can support even that. And so that's why we propose the solution. Even if you want to add some correlation also, we can add it without any problem, and the solution still work even for this consideration. That's why.
Do you think there would have been other reasonable ways to model the same problem?
Yeah, probably yes, but for me, I think it was.
Okay, and you are kind of happy with your chosen methodology that it's providing?
I think because the solution is easy after all. Just you get a policy, you just apply it, and you evaluate it, and probably you can just correct with model predictive control, and then. So I think the solution can be very efficient and easily used for any operator. So you will not keep calculating all time. So this is the importance of the methodology. For, I don't know, even if we want just to solve this problem online, I don't know, for an MDP I can use Q-learning, but the problem of this methodology, they need a lot of they need a lot of time in order just to model well the problem. They should visit the state a lot of time in order to get a track of the probability transition, and so the learning phase will be so important. Probably if I apply it in my model, it will take me probably 1 year or 2 years in order to track them and say, okay, things will change in 2 years. The prices will not be the same. The process is not stable on the long period in order just to do it online. And so just I predict, even if I predict with errors, sometimes it's better to do some offline with the errors of prediction than learning and I don't know, because especially when you are doing some trading, if you said, okay, I will sell in the minimum, even if there is some variation, you decided to sell, you will be winning, you see. So
yeah, regarding your models, so how difficult they were computationally? Was it sort of just a few seconds to solve things, or did it take hours to run?
For the short term, probably 1 second, I think, just to have the solution. For the long term, because I should calculate the short term for all the combination of the battery age, the sizes. So in the case of lithium, it takes probably 8 hours with a normal computer. So on MATLAB. In the case of lead acid, because the state of charge levels are not that much, it can be achieved in 4 hours. The solution.
Okay.
And so you make it, you can assume, as I said, more correlation probably between the prices. And after all, I think the maximum possible case, maybe it will take you 1 week, but you will apply it for 6 months, so it's great.
So if you would really start doing something like this in real time, in the real network, you maybe partly touched that in your perspectives, but somehow if you would really sort of try to do this daily, how close are you with that, with your models? Would these more or less be adaptable to really production usage, or would you need something rather different to do that?
I didn't understand what the question
So that
was.
you would have this kind of system running in the mobile network, which would at each time instant decide what to do.
As I probably if I have some error of modeling, I can also define some threshold and decide if I, at the beginning of the day, I decide some threshold. Imagine if I find myself, the policy tell me, okay, now you have to buy. But I see the prices and I see that there will be big variation between the predicted value and the real value. I compare the real value probably with the threshold, and I see if I'm above the threshold, I keep buying. If I'm under this threshold, I do nothing. Probably is better. So I will not apply it without seeing. I see the reality. Then I probably add some threshold values and say, okay, I apply if the real prices are above or not. So I should combine it with other methods also.
So are you saying that with your models you would just get some sort of threshold value? And then momentary decision making would be just sort of very simple comparison.
The problem, because this if I want that to get the threshold value, I have also to predict the prices already. So the threshold assume that I know the prices. So it's better to apply my method because also I know the prices, and so it's better probably to do the right action. The threshold for me, it will be probably based on more heuristic data. So I try just to see probably the prices on a long period, and really I decide based on that. You see, so it cannot just be because if I know the real prices, I just apply my method. Is better. So why doing a threshold in that case? So the threshold should be coming. The value of the threshold should be coming from another suppositions, another model probably.
Yeah, but then when you are in real life, then we don't know now what happens after 5 minutes for sure.
Yeah, for sure.
We have sort of
Yeah.
estimates of that. I
Yeah.
guess.
In fact, for me, I'm just estimating the average prices per hour, and also the choose of the hour will allow me to estimate the prices with higher accuracy. If you ask, we can like estimate really well the prices on a hourly basis, and also I have this problem of the battery charging and the charging rates, and so if I want just to charge my battery for 2 or 3 minutes, the impact of this action would not be that much important on the gain that I achieve. So that's why an hourly decision will help me to predict and just can take into account the constraint on the battery too. So that's why. So if I charge probably by 1% my battery in 5 minutes, I will not have a big impact of selling it later. You see, so it's about more the amount.
You are dealing with averages. I guess it's on the average maybe okay.
Yeah, it's the average.
But no. Then somehow days can be very different, especially with the renewable generation.
Yeah, for sure.
So could you think that doing something different than dealing with the averages would give you better results?
Yeah, it could be. It could be if I reduce more. If I reduce, example, the decision time by 5 to 5 minutes. Something like that.
Or you would maybe consider the weather forecasts and that kind of components to get a better estimate what is going to really happen in the next few hours.
I think it can be better for sure if I reduce, but it's assumed that my prediction are accurate. So if my prediction are bad in 5 minutes, so there is no. It depends of the accuracy of your prediction. So if I can predict the prices with high accuracy within 5 minutes, yeah, great. I apply the same method with 5 minutes, and so it's better for me. So instead of I can charge the battery to 70%, I will just stick to 10% in 5 minutes or 5% in 5 minutes, 1, 2, 3, and I will have better gain for sure.
And do you have any gut feeling how much better you would be able to get to that in comparison to the average? Would you gain enough to make it worthwhile?
It depends on the variation between the prices. This is the thing. So if the prices stay close to the average, I will not gain that much. Probably if the variation between the. But the problem also there is this battery energy charge and discharge efficiency. So if I'm losing, so I'm losing also the processes. So probably not gain. So it depends if the variation of the prices within 1 hour compared to the average are very, very high, then I'm gaining a lot of money. So it depends on this value probably.
Right. Okay, then a couple of very detailed questions. So you had this exponential versus incremental increase in your growth scenario. So what is the reality? Is it sort of do we know how the growth today, which of these is sort of more matching?
Because in fact we know the average value, the average growth generally. We have some values on the average growth. Here I assume 2 models. After all, the problem, it depends from a site to another. If you are, example, in a site and there will be a real estate project here, the traffic is growing, and also maybe, the traffic is growing, probably, your consumption is growing, but probably also the operator will install another NodeB. Right. So the traffic, you will share this traffic. So it is dependent on the site. So you cannot just compare a site in an industrial zone because probably even the traffic during night will be 0. In some urban cases, the traffic at night because everybody is in his home, so it depends from site to another. So it's just a model. So for me, you should for each site apply your prediction and your prediction of price. So it depends on the site, and I cannot have the same result for all the sites.
So in the ideal world, you should actually have a more accurate model, which would be tailored for the history of that particular site.
Yeah, probably if I get just some model for a particular site, I can compare probably some industrial.
Would that be easy addition to your model?
It will change anything in the solution, but if I find some data, some interesting data, it will be interesting for me just to work on that. But
good.
Yeah, but for me, I wanted really to present a model that can be applied for many, many cases. So even I can example, especially because the transition probability example for the long term was taken deterministic. You don't have to do a Markov decision process to solve that. But I proposed Markov decision process in order even just to take into account some other parameters, some other transition probabilities. It's just to have something very, very general.
Yep. Yeah, and of course in the modeling in general you have to make a lot of assumptions.
Yeah, and
sort of,
yeah.
That what if you make slightly different assumptions, how would things go?
Here just I suppose that it's just the data rate who are growing. And so the data rate, the same population is here in this region. Here is more, okay, the data rate are growing, but the population also is growing. And so if you see the here, so the growth will be, the difference will be much seen more in the last years. So I assume that. But.
Yep.
The average growth here is even 20% per year. And if you compare to Cisco values, in average worldwide, I will have 44%. But 44%, if I take the traffic after 10 years, it would be 14 times more important than the peak traffic now. And so to deal with that for me is just installing 2 or 3 base stations or just diversifying more the network by adding some AtNet, some femtocells, some small cells.
Yep. Yeah, so, then very detailed question actually.
Yeah.
I guess you didn't show it there, but when I was reading your papers, it was one of these charts which I tried to interpret, page 59 on this draft of the thesis, which has these blocking probabilities.
The blocking probability. Yeah, I called it
13.
blocking probability. Yeah, okay. Yeah.
Yeah. So I tried to understand that what is a blocking probability and why do they happen in the evening?
In fact, the blocking probability for me, it was the probability to have requests from the grid to stop consuming from it. I called it blocking probability.
And how did you get that from a data set, or how did you get
in fact, till now, this blocking probability will be very, very low. So Orange, they have some project with, it's called Activity. And I think the problem they ask them, but this contract is with data centers, and they ask them to reduce their consumption probably 3 or 4 times a year. Okay. So here it is the case if we suppose that this right now probably we are not more really implementing demand response very highly now, but probably in the future we will have more incentive to do this demand response. And I assumed it from if you see some houses the night, because the houses just are on, and so there is more lighting, there is more heating, and so we will consume more, and so probably the blocking will be higher compared to that.
Okay, so it's kind of your estimate.
It's my estimation.
In a way.
Yeah.
Because
so
somehow I would imagine it would correlate a bit of the energy price. That when the energy price is high, you will have more blocking. Yeah. While it's not doing exactly that.
No, I didn't take the same thing, because if I take the same thing, it will be the same strategy after all. Yeah. So if I get the same curves.
Yeah, but then one more mystery for me was when I compared this picture 313 to the 314.
Yeah, 314, okay.
Yeah, so in the 313 we had sort of maybe 1, 2, 3, 4 valleys in the curve. Yeah. And then in the figure 314 we had just 1 valley, or maybe 2 valleys, depending a bit. Yeah. So what explains this, that you have sort of a different number of valleys in the different?
It is because the battery capacity. So the first one was for 16 kilowatt-hour battery, and we know that the base station consumes between 3.5 and 6.5 kilowatt-hour, and so 16 kilowatt-hour battery will allow me to be in self-autonomous mode between 2 and 3 hours. For 48 kilowatt-hours, it will be between 6 and 8. And so that's why here I will have valleys each 3 hours. Because what you do in demand response is just when you have the when you say, okay, I don't have enough reserves in my battery, and the grid ask me for stopping consuming, I will charge my battery in the maximum because I'm already paying the penalty, so it will not change anything, even the prices are high. And then try to be in self-autonomous mode for the longest period possible. So that's why peak 3 hours, each 3 hours I will have the peak. And for the other one, 6 hours, so it's more...
Okay, good. And maybe my final question, so now when this 5G is coming,
yeah.
So what would change in your analysis?
I'm just focusing on the RAN, on the radio access network. Probably the consumption will not be the same. For services, because there will be more services, the traffic will be more increasing. But I think the model can be also applied for any kind of network. And because I'm not really dependent of the technology in this work, and also the work was applied for a base station, but it can be also applied for a households or any facility working with a battery. So
and the fact that you would have thousands and thousands of IoT devices under the base station wouldn't change much. Or the very low latency requirement maybe are some of the issues that are there in the 5G.
For the energy, IoT, I don't see really the link, to be honest, because after all, if I define for each equipment probably a battery, I can, or probably okay, we can exchange. Example, we can extend the work in order I define example of battery for this base station, another battery for this base station, and I make kind of correlation between them and probably some exchange between them, and probably I'll allocate more traffic here and here, so probably the work will not seem the same. So, or probably if I have a small femtocell, I will allocate part of the traffic if I don't have enough energy in my battery. And so I don't have just to buy electricity with high prices. Yeah, we can extend that problem probably in multi-case scenario, because here I just consider it one base station, but we can make a network and then try just to simulate many battery for each network and cooperate together.
Yeah, because now with the 5G sort of coming, I guess your work is even more important than today, because the estimate, I guess, is that would sort of multiply the energy consumption of the network by 3.
Yeah, for sure. So
and
after all,
any of this kind of work that provides some savings there is very useful.
Thank you.
So with that, I guess I'm through with my questions.
Thank you so much.
Thank you. Okay, so let us move to the second referee. So the second referee is Professor Tuffin from IRISA.
Thank you. So I have to say first that I really enjoy reading the document.
Thank you so much.
Very nice and much really quality above the average quality that I've seen during the past years. So it was a nice one. I particularly liked the introduction that was presenting very well the challenges and the contributions. So for me that was very clear from the beginning. And it's good when you read it to have this vision. Okay, so I will have less questions than Luca, because otherwise you will miss his plane. So what's interesting in your work that you have a short-term optimization and a long-term optimization. Do you use the short-term optimization in the long-term optimization?
Yeah, for sure. In fact, the short-term will allow me to calculate. The short-term will allow me to calculate D. So D, it depends. If I don't have any battery, I will calculate D based if I'm powered exclusively by the grid. If I have a battery with a certain age, I will do my short-term optimization, calculate the daily expenditure, and include it here. And so to establish the long-term, I should calculate the daily money spent by the operator for all the configuration of my sites. So all the battery sizes, all the calendar age, all the cycle age. And so that's why, and they are correlated with each other. And the long term impose some parameters on the short term, the size of the battery, the cycling strategy of the battery. So the link is reciprocal. I have a reciprocal link between.
is the short-term optimization optimal for the long-term optimization? Because you don't use the short-term, if I'm right?
Yeah.
You don't have this degradation. You don't use the degradation of the optimization.
I use no. In fact, I calculate the cycle age and the calendar age of the battery, and I pick the degradation of the battery. I include it in the short term, and I calculate based on that. So yeah. So the degradation is included, but for the degradation, because I'm just optimizing on one day or just on one semester. So yeah. Sorry. I assume that the energy efficiency remain the same for the whole semester. So I just pick one value and calculate based on that. So without any problem. But from a semester to another, it can degrade, and especially with the number of cycles that I perform it. So it depends on that. So it's more.
Can you just for a reminder, or it's this slide? So you use an MDP, and your transition probability, all state transitions are deterministic.
Yeah.
So it looks like nothing is random.
Yeah, for sure. I did the randomness. I included the randomness in the African case. Here, I can include some randomness if I consider the daily prices profile, but the whole profile as a state. And then I can even establish some correlation between the prices the semester before and the semester after. And that's why you use the MDP, because we can extend even the work if we assume randomness, but the solution will work even if we assume randomness. But the problem for the states that I choose, if I decide, okay, to install a battery of 16 kilowatt hour, I will find a battery of 16 kilowatt hour. I cannot find another setting. So for the equipment variables, their transition is really deterministic. But for the environmental, outside environment, probably variables, the prices, the electricity prices, the user traffic, or I don't know, probably also in Africa the grid improvement, reliability improvement. So they have a randomness, and they can include it without any problem.
That probably answered also my other small question about prices for you. In this model, they are constant. They are fixed, not constant. Deterministic.
In fact, on the long term, real prices, they have a probability to be equal to the average prices, a probability to be equal to the values before and above, and the probability to be equal to some values below. So there is more randomness in the short term.
And it's related to the Lucas question. So if you don't follow the average price success, if you have some variations in impact, you can moderate in your NDP by.
If I assume, I just should reduce the decision time. Just reduce the decision time. I try to track them for a lower decision time. Example, taking 5 minutes, and I apply the MDP for each 5 minutes. I have a new decision. So probably I can track them more. I don't know, but.
So in your perspective, you were saying that you want to base your result on real data.
Yeah.
So I had the feeling when I was reading the thesis that you had a lot of real data.
No.
That's why
No. In fact, I assumed a lot of real data from. I took Quebec spot, so I got the prices, the spot prices. But from the spot prices, I assume that I have some the real prices. But the assumption is based on just an assumption. The assumption is from me, but I got the. In fact, example for the prices, I got them from Apex Spot. But for the prediction on 10 years, because for prediction on 10 years, I just assumed that I know the prices for 10 years. But just the 4 years, the 4 year were based on heuristic data, and then I assumed that I made a prediction for the next 10 years. But we can establish some model for prices forecasting, and I just assume it's a model example in Denmark that the price growth will not be the same compared to Europe. It's very, very hard to predict the prices in 10 years because...
Yeah, but in terms of your analysis, I mean, it doesn't bring any complications?
It's just another work apart. So after all, just as I told, just you make your forecasting, your prediction, then you make your classification, but then just you change a little bit on, just you make the action more complex by defining a maximum number of cycles to be performed per day for each class of the system. So, but after all, it remains the same. So I will not have any change depending on, but it's another work apart.
Yeah. And if I got it right, you model in your model you abstract your network as a single node, right?
Yeah.
Yeah. So what would it make as a difference if we had a different topology with different demands on all the different areas and so on in terms of the analysis, and in terms of the modeling part, and especially if you were talking about 5G.
Here, as I thought, it will. If I will consider, example, a lot of equipment, I can, example, consider some equipment with batteries, some equipment no, and have just to find a good compromise between them, see the electricity prices. If the prices, example, are high, I can allocate some of the traffic to the NodeB example with a battery, because it can use this battery. It will be more complex because I will just multiply the number of states by, I will just power the number of states by the number of NodeBs in the short term. So if I want, so it can be doable with MDP, but just it will take more time. It will not be just 1 second. Example, if I have 10 base stations, in my case, I'm having 3,000. In my case, I'm having just 200 states, so I should multiply some of the states, especially the battery. So if I assume that I have, example, 20 state of battery, the prices should be the same. Well, probably the traffic will not be the same. And so, yeah, the traffic will be just power of n, number of nodes. The prices will be the same. And the number of state of charge of the battery will be power of n. So the number of states will grow very, very fast. It may be that MDP will not be a good solution for that, because especially for processing, because I need a lot of processing power. But we can also sometimes, even if you have a big states, I worked on that before, in some region, some states are not, they don't have a big probability to appear. And so you can assume sorry if I go into detail, the transition matrix null equal to 0 in some cases, and just take the values when the transition matrix is not 0, and then reduce the complexity. We can play on that on the coding, I think. I succeeded before probably to make an MDP for some cases with 20,000 states and 112 actions, but with playing on some parameters in the code.
Okay, thank you.
Thank you so much.
Thank you, Bruno. So let us move to the questions of Dr. Benjima, who is with Orange Labs.
Okay, thank you. So I don't have a lot of questions left, but it's good because I will be short. So just to come back to the question that has been just asked. So you have been working on a site level.
Yeah.
If you said before that, okay, if the load increases, then the solution would be to have more sites. But this would consume more energy. So how do you see your model extended to a network? Knowing that at a network level you will have this battery management, you will have densification options, for example,
for sure.
and you will also have this sleep mode
yeah,
option.
to be included.
So how do you imagine things by combining all this?
Combining, yeah. So I assume the example in the African model that the growth will be 20% per semester. So I reached the point in which the peak traffic would be 14% of the actual one. So I just assumed at the beginning, okay, I will increase the bandwidth, I will increase the number of antenna for a certain until a certain level, then I will and then I have no other choice by installing, doing some densification of the network. And in that case, it depends. Okay, just here you will have in that case a lot of nodes, and each node have his state, the state of its battery, some traffic which is allocated to them, but probably the action individually for the battery will be the same. But I have just to add some actions to make the network cooperate with each other. So probably some action I will take 20% of the traffic and allocate it for this base station because it has better battery level state of charge left. So it will be another problem, I think.
Huh? You imagine a collaborative process, and you talked about classification. So in this case, for example, you said earlier that if you have a network level, you will have a more complex problem but you may have some states that never happen. Don't you imagine also in that context that you can classify cells or sites, and this allows you also to reduce your dimensionality? You will have
probably some kind of cells, so I can apply the same strategy for them. For sure. It can be for sure. By putting power in.
Do I have 2 minutes? I think you are short.
Yes, it's okay, 2 minutes.
Okay, still one question. I have
sure.
Still 3 questions, but I will ask only one. Just the traffic curves that you showed earlier. I don't understand.
The traffic increase.
Yes, what is, because a node is always between 0 and 1, and it cannot increase exponentially.
I put 600% of the maximum load.
What is the user something?
User traffic load. I took it 600. In fact, the value of 1, if we assume it is the peak hour, so the load in our case, it is the actual traffic divided by the maximum traffic at peak hour. But the peak hour in our case is because is taken if 16% of the users are active in the cell. So 100%, if I have this traffic, 600%, I should think about, probably in 10 years, so the traffic will grow. And so my new peak will not be the ancient peak. It will be 6 times more important than the actual peak.
Traffic demand and not the
So 600 is the peak hour in the first year. Then 600 probably the peak hour in 10 or 12 years.
And one last question, very short. When you talk about hierarchical decision, I didn't understand very well what happens with trading. If you trade on the short time, then you need to consume more cycles of the battery, but the number of cycles of the battery you are allowed is calculated on the long term. I see there more joint optimization rather than hierarchical thing, but
I will show you probably this example. Lead acid. This is the long-term strategy. So here, a lead acid battery will allow me to perform 1,800 cycles on 10 years during its lifetime. So it is, if I take example, if I calculate the number of cycles that I did here, if you calculate them, is 10. So multiply them by 1,180, and I will have 1,800. And so, in fact, in the short term, I will install my battery. So I know my battery will allow me 1,800 cycles. I can decide, I can make 10 cycles in the first semester. Buying, I will win a lot, but my battery cannot be used and should be removed. And so here, on the long term, I decide, I choose the number of cycles semester by semester. in order just to maximize multi-CU. Yeah, and then I get this value. Example here, I got like a constraint on 2, and I inject it as a constraint on the short term. Then I calculate the average number of cycles that I achieved, because in some cases, probably I don't achieve exactly the same, and use it to calculate the new cycle age of my battery. And then I recalculate, and that's why it's more hierarchical than combining, because I'm not in the same level of decision. One is 1 day, the other is 6 months.
So, thank you.
Thank you so much. Yeah, sure.
Thank you.
Okay. Okay, thank you, Sana.
Thank you.
So now we are going to ask your advisor to express their opinions, maybe not these questions, I don't know. Starting with Professor El Ayoubi.
Thank you. So I would like to thank you for this collaboration for 3 years. It was very instructive for me. I just discovered many fields that are different from the field I'm working with of mobile network engineering, smart grids. But it was very, it took a long time of your PhD work to look on details on battery technologies and compare them and so on. I don't have a question, but perhaps as you explored several fields, you worked very lot on mobile network engineering, so it does not appear clearly in the PhD, but you have tested many sleep mode strategies, small cell, head nets, more antennas, and MIMO, and so on. So you are an expert in this. You also investigated energy grids and battery characteristics and so on, and you worked also on investment planning on long term. So which of these fields do you think that it's more interesting for you if you have the freedom to work on, and in which field you think that you have produced the most innovation?
Well, for this PhD, I think it was more about the smart grid field. So after all, just the telecommunication part entered only in my consumption model. So I just used that as just a consumption model. I assumed the traffic. So it can be also, as I told, applied on any other facility. But I don't know, I really like telecommunication before I worked on standardization also. And I think it's a great way also to combine both. Especially if we know, about communication, if we can model the new consumption, if we include some new features. So it can be very, very interesting if I combine both. Why not just working on both? Also on the investment, money is so important.
Okay, thank you. So we finish with Professor Shael.
Thank you very much, Samson. So I also want to first congratulate you really for today's presentation, for all the work, for all these years. I wanted also to thank you very much. It was very instructive for me also. Lots of exploration, many fields, many tools. You were very focused, very involved, lots of works. It was a little bit maybe tough for you sometimes, very hectic, but overall I think it was really interesting and for me very, very enjoyable. Thank you so much.
Thank you. That's the same for me. Thank you.
Merci, Samson.
Okay, so Michel had a lot of questions, but you have time constraints, so maybe we pick one or two at random. I don't know. Okay, there are so many. Okay. No, I need to compress. No, that's true. A recurrent question. Okay, for me, something I didn't get is that you test, for the performance evaluation, you have tested all your algorithm on a given price profile.
Yeah.
And you have no idea of the impact of the profile. Is that right?
The price.
You have no idea, for instance, you have a certain gain for a given profile,
Yeah.
which is apparently the expected of the expected price. But the question is, what is the impact of the profile price? So the question is like this: why have you don't have tested some? You take your average price,
Yeah.
you add some noise,
Yeah.
simple noise, additive noise, and then you look at the impact, for instance, of the variance of the noise
Yeah.
on the gain. Just a simple thing like that. Okay?
Yeah.
Something very simple. Have you tested this?
I
You don't need real data for that.
Yeah.
You can test, and at least you have a conclusion about the gain.
Okay. In fact, the gain depend. Example, if I'm doing trading, the gain depend on the difference between the minimum and maximum price. If I'm making one cycle, it is depend on the difference between the first minimum, the first maximum, the second minimum. If I'm doing two cycles, if I'm doing trading.
If you want to get to the point, why are not you don't have quantified this? This is my question.
In fact, I worked on that on a journal, on the first journal paper. The problem, the journal paper and the first conference, I didn't put them in the thesis.
Okay.
So in the first two papers, I didn't consider this cycling constraint, and I included some renewable energy in them. And at the end, I tested the robustness, but in that case, I got the same electricity price model and the same traffic model, and I added to white noise on the real value, and I quantified the variation between the prices compared to the variation of that, and also the number of state of charge decided, because for 48 kilowatt hour I decided 61 states, if you remember. It was a result of this paper.
So the conclusion, assume you have SNR of, I don't know, 5 dB. The gain is what is divided by 10%, 5%, this kind of things. Can you say more about it? Because it's always, what you're saying is more like an intuition. Okay? But I can have intuition before reading your thesis, you know. So that's why I say, why have you, can you say something? Say, okay, SNR is 5 dB,
5
then
dB.
the gain is...
My SNR here, should be 5 euros.
No?
5 euros.
No, I don't know.
5 euros or 10 euros an error.
What do you use? The gain will be divided by 2 or just 5%? That's the question, the sensitivity of the gain to the... It's a robustness, if you want.
In fact, the gain, the problem when I got the average gain, I didn't find that there is a big error between the expected and the average gain. But if we take the variance of the gain, sometimes I'm winning more, some days I'm losing more. And so I didn't really know how just to say an average. An average, it was really, really very close. But then just the variance, okay, sometimes I'm winning, sometimes I'm losing. And
okay, so second question. Is more like you have not compared to other policies, okay? Because like, as Yuka said, there is a lot of work. People have applied MPC for batteries in the transmission network. There are many works, okay? They have applied this for microgrid, etc. So you have not compared. So my question is why you don't have compared with other works, and second thing, why you have not compared to naive strategies, and this is one strategy selected by Yuka, the valley filling. Okay, so the question: if you do the valley filling, what is the loss? Do you lose a lot? Because the nice thing with valley filling is that it is not sensitive to the utility functions, to the accuracy on the parameters, etc. So what do you what is the gain with respect to these naive strategies? I'm surprised you have not compared to them.
I didn't,
so
for sure.
What was your motivation?
In fact, I'm for the setting that I chose, my optimization is optimal. So I verify that my Markov chain is ergodic. I don't have a periodicity between the prices. So if policy iteration can work and give the optimal policy and optimal solution for my case. So if I compare to some naive price methods, the problem I will always find myself better because of the setting. But even with the errors, I tried just to compare with a threshold case, and I found that I still better. And
you still better, but but how much you still? If you compare valley filling, okay, and to the MDP, or dynamic programming, okay?
Yeah.
And
Yeah,
the
for
gain
sure.
is 10%
Yeah.
when everything is perfect.
Yeah, for sure. And if there is an error,
That's
so
the
yeah.
question. Better, I'm not surprised because you have those.
Yeah, for sure. And for
By
MPC,
how much?
for MPC, after all, like I didn't take MPC. Why? Because I assume there is in the model at the beginning. I assume there is no correlation between the prices. So if you increase by 1 hour, it's not you will not gain anything with doing MPC. Other thing is better to predict the prices using the slot prices, the spot prices and retail prices 1 day before. So they are published around 11 p.m. in Europe. And so I think it's better just to predict your prices just for the day after. And don't extend your prediction. Example, after 1 p.m., okay, I did one choice. I should predict the prices in the next day. So probably this accuracy will not be that good. So it's better just to stick, come at midnight, predict for the next day, and then the other day get the day-ahead prices and repredict for the other day. So you don't just increase your prediction from an hour. Yeah, I tried just to apply model predictive control, to be honest. But this was, it was a choice after all. But I proposed probably it's better to apply model predictive control on the long term. If we assume correlation between the semester, the prices in this semester and the next semester, probably it's better. But for the short term, I think just getting the spot prices, retail prices is a better option for me. Better than, sorry, but.
I think I need to stop. Mr. President, you need to stop. Okay, so thank you very much. And where shall we go? We stay here?
Yeah.
Okay.
Sure.
Okay.
Thank you. Thank you so much.